Okay, let's begin lecture number 6 on neutron diffusion. This is week 4. This is part of the course NE402, Intermediate Nuclear Engineering. It's an advanced undergraduate or a graduate level course in nuclear engineering covering neutron diffusion, radiation transport, and Monte Carlo simulation. So it presents a unified picture of all three methods, two methodologies, one deterministic and one stochastic. And my name is here, my cell number, my personal email, official email, and my personal website. As I said before, I would be more than happy to take your questions and suggestions. And of course, I'd be very happy if you spare some time and send me feedback, preferably on my yahoo.com, whether you like it, you don't like it, what you feel is missing, what you would like to be added, and did you follow it easily or did you find any difficulty? I'm trying to make it as simple as possible and focusing on the concepts and the application in engineering of the concepts. So let's begin with this deterministic model. Now, I just said to you that there are two ways of looking at neutron transport, neutron interaction with matter. One is a deterministic methodology and one is a stochastic methodology. In this course, I'll spend a few weeks on deterministic methodologies and another few weeks on stochastic, and then we'll do some applications. So let's begin with the simplest of models, which is a deterministic model that describes neutron behavior in a system. And it's not as difficult as what I'll go through in the chapter following this one. That is the integral differential Boltzmann equation and the integral equation. This is just a differential equation called the neutron diffusion equation. And let's start with a very elementary form. So let's look at a cube. You know that a cube has 6 sides. There's X, Y, and Z, so it's got 6 planes. Now, as I said in the previous lecture, certain things cross the surfaces, and in this case, it's the current Jx at X, and this is X plus dx, and what's coming out of the other side is Jx plus dx. I told you in the last lectures that J is a current. It has the same units as flux, neutrons per centimeter square per second. The only difference between current and flux is that this is a vector. Flux is inside the volume, like collision density was inside the volume, and what's leaving is crossing a window or a door. That's how you enter a room. You cross a surface and enter a room. So you cross a wall to enter a room. So a neutron crosses a surface to enter a volume. Okay. So now what we're going to do is we're just going to count things coming in and going out. So let's look at the left boundary. What's coming in is J in times A perpendicular. Now, if this is X, that's Y, and vertical is Z-axis. So what's coming from the left in the X direction faces this vertical wall, which is actually dy times dz, and we'll call that the perpendicular area. What's leaving is J out. So J in minus J out is the net crossings. Then we're going to lose some neutrons in the volume, which is volume in element delta V. The number of absorptions that we're going to have is sigma A times phi. So sigma A has units of per centimeter, phi has units of per centimeter square per second. So this has units of absorptions per cubic centimeter per second. When I multiply it by the volume of this box, which is delta X, delta Y, delta Z, then I'll be left with interactions per second. So this is also crossings per second, this is interactions per second. Then I could have a neutron source inside the box. So let's say if I've got S, X, T, delta V neutrons per second inside the box, then here's the balance equation. The change in number of neutrons per second, because the units of n, remember what is small n? Small n as units of neutrons per cubic centimeter per second, because the definition of flux is n times v, small v, where v is the speed of the neutrons. Now in this model, I'll call this the one group model. What I'm assuming is that the speed is not changing even though interactions are taking place. So what you see on the left side over here is, in terms of units, it's neutrons per cubic centimeter per second multiplied by cubic centimeter. So it's neutrons per second, increase or decrease in the box. Now, I would like to develop a theory, so I've got to simplify. And one excellent source for this is the book Lamarche and Barata, 2001. I grew up studying Lamarche, Henry, Duderstadt. And when I did my master's, I studied Bell and Glasgow. And when I was doing my PhD, I used all of these books. But mainly these four books, I still have them. They were the center of my life. And whatever I've learned has been mainly from these books, plus lectures from my professors. I learned a lot in nuclear engineering, mainly from three professors to whom I'm eternally grateful. Professor Mike Williams, Professor Jeffrey Lewins, and Professor Charlie Maynard at Queen Mary College, London, University of Cambridge, and University of Wisconsin, Madison. With so much affection, they taught, and me and my class fellows learned, and I'm passing it on to. So this is the conservation equation. Now, remember, when you talk about conservation equations, there are three. There's the conservation of matter, there's the conservation of momentum. Momentum is a vector, so 1 plus 3, 4 equations. There's the conservation of energy, so these are 5 equations. What you see, equation 3.1 is a scalar equation, so it's only one equation. Now, I would like to simplify this. So let me say that J out, what's coming out, is what's going in plus the derivative change. Now, the divergence of J, grad is a vector, J is a vector. So when you dot product two vectors, what you get? You get a scalar. So, so here's the divergence of J multiplied by delta. Now, the diffusion equation over here comes out to be dN by dt is minus the divergence of J. I've just written it J because now we're just talking of J. The J ins have cancelled out. And so the divergence of J minus sigma AV. Okay, so what happened to the delta V? So because it got the A perpendicular replaced the delta V because there's a divergence now. So this is the equation that you've got. The delta V's are cancelled out. Now, if you look at equation 3.3, it's got two variables. It's got J and it's got phi. Of course, N is the same as phi because phi is NV. So you cannot solve one equation with two variables. So you need a connection. You need a connection between J and phi. And as you saw in the previous lecture, this is exactly what Fermi did. He used Fick's law or Fourier's law, and that's cause-effect relationship that J is minus D grad phi. So J is a vector, grad is a vector, phi is a scalar. Now once I put this over here, so if I put here minus D grad phi, then of course the D should be inside, but let me assume now that D is independent of position. So I take it out, and the del dot del becomes a del square, so it becomes a Laplacian. Now the divergence of a grad is a Laplacian. This is what I always like my students to know the names of these operators. This is a divergence and this is a Laplacian. So I get D del square phi. Del square phi is a scalar. Minus sigma A phi plus S. And here is the time dependent neutron population equation, 3.4. let's look at the steady state equation. The steady state, I'm going to put dN by dt equal to 0. So I get what is called the steady state one group neutron diffusion equation with a fixed source in here. So here, what we assume is that the energy does not change. So phi is just a function of position. Now, let's go a step ahead and say that if there are two energy groups, then what would happen? By two energy group means that all the neutrons in this problem are either fast neutrons or thermal neutrons. Again, not a very good idea, but let's just start with it. So you'll see that a two-group model is not bad. There's a lot of research that uses two-group models. And of course, these days we've got very powerful computation. So you can take 262 groups, and Monte Carlo simulations are actually done with so many groups in the multi-group case, or they're done in the continuous case. And we're going to go through all that. For the time being, let me just write a two-group model. Now, in the two-group model, I'm going to say that group 1 is the higher group. It's got more energy for neutrons. Group 2 is the lower group. And I'm going to assume that neutrons which collide in group 1 can come down to group 2. But neutrons which collide in group 2 cannot go up into group 1. Okay? Now, if you just bear with me, of course, you might say, but what if there's fission in the lower group, and fission is thermal fission and it produces fast neutrons in the first group, so why are you not considering that? Well, I'm going to do all that. Right now, let's keep it simple. Let's say that it's a non-multiplying problem, so there's no uranium or plutonium in this formulation. It's just a fixed source problem. Let's call it a fixed source problem. So, so again, let's look at this equation. This was that source minus the loss terms. So if you say I can write this as minus d del square phi plus sigma a phi is equal to S. And that says whatever is the source is equal to the losses. So leakage term, loss term by absorption balances out with the source term in the steady state. Now let's look at the fast group. What's happening in the fast group? There's leakage in the fast group. Fast neutrons could just leak out of the boundaries. They could disappear. So the fast source minus the loss term of the fast neutrons minus the leakage of the fast neutrons is 0. So here is a balance equation for fast neutrons. Now, let me just look at the loss term first. The loss term says that there's a removal from group 1. Now, how can there be a removal? So let's look at this over here. Imagine that a removal from group 1 is a capture in group 1 plus a scattering from group 1 to group 2. So sigma R1 phi 1 is the number of removals per centimeter square per second from group 1. Sigma C1 phi 1 is the number of captures per cubic centimeter per second. The scattering out term are the number of scatterings which are leaving group 1 and entering group 2 per cubic centimeter per second. So group 1 has nothing coming in from group 2. But group 2, as you see over here, group 2 has source minus a capture term minus a leakage term, all in group 2. Now what about this source? Now this source could be a direct source, and S1 could be a direct source. You could have a fast neutron source over here from californium 252, as I mentioned, americium beryllium. You could have an MB source, you could have a CF252 source, which is giving out NEV neutrons. The source in group 2, because usually we don't have a thermal neutron source, so the source in group 2 is that which is slowing down from group 1, and I multiplied by P to tell you that these are the neutrons which have escaped the resonance. So P is the resonance escape probability, and if you remember, I think it was lecture 2 or lecture 3, where I took you through the 6-factor and the 4-factor formula. So in the 6-factor formula, I showed you precisely where the resonance escape comes in. So if you've forgotten that, so please go back to, I think it was 2 or 3. So lecture 2 or lecture 3. Look at the cycle. So this is S1, the direct source. This is S2. Now what do I have over here? Now 3.6 and 3.7, I'm just talking about fixed neutrons coming in here, a fixed neutron source. I'm not including fission. If you want to have a fission, for example, if you have a multiplying medium, then the fast neutron source would be the fission neutrons born in the fast group due to fission reactions in the slow group, mu sigma F2 phi 2, plus of course fissions that are happening in the in the fast group. And of course then we'd have to multiply this by the by chi of E, which is the contribution in that particular group. So for the time being, let's just stick with 3.5 for the one group case and 3.6 and 7 for the two group. As you can see, they don't look very difficult. They look as second order ordinary differential equations. Now, let me spend a few minutes looking at the one group diffusion equation. Now, the one group diffusion equation can be obtained analytical solutions. By analytical, you know that it means an exact solution, something that I can look at, it looks nice, and something that I can easily program. I don't need any numerical method for it. But the problem with analytical methods is that they apply to what is called regular geometry. Now, if you look around you, you won't see a lot of regular geometry around you. You'll see things which are regular, okay, but there are things which are not so regular also. So let's take ourselves to regular geometry first. And let's start with non-multiplying systems. So let me say from the beginning that the one group model is too simple for practical application. So even though it is too simple and even though it's not a very practical application, it still has an academic value and we need to understand it. Why? Because it gives considerable insight into very important neutron characteristics of nuclear systems. For example, an explosives detection system does not have any multiplication. It's got a fixed source and you're just looking for an explosive, you're trying to identify materials. So for systems which are predominantly one group, now I told you about fast reactors, you saw that there's no thermal spectrum in a fast reactor. So I could say that it's a one group reactor, okay? And you should not have a lot of objection on that because a fast a fast reactor does not have thermal neutrons. So there are cases when you can apply a one group equation. And if I state them, then those cases are where the neutron spectrum is predominantly fast, okay, or even thermal. If you're looking at just thermal neutrons, then don't look at the fast neutrons. So it is used with the appropriate average nuclear data to obtain the neutron flux. From the flux, you can get so many reaction rates, you can say things about the criticality, you can say things about the thermal power of your system. Now, let's look from the mathematical point of view. So the neutron diffusion equation, which I just showed you, 3.5, is a second order ordinary differential equation. And you can solve it if you know the boundary conditions. Second order means that you need two boundary conditions. They could be Neumann, Dirichlet, or mixed boundary conditions. Now, as you know that a Neumann boundary condition specifies the derivatives of the quantity that you're trying to get. For example, the derivative of the flux. So if you've got symmetry and you say d phi by dx is 0, so that would be called a Neumann boundary condition. If you say that you know the current entering a particular surface, then that's a Neumann boundary condition. If you do not know the derivatives, but you know the values of a function, in this case the flux, on a boundary, then you say you've got a Dirichlet boundary condition. So whatever it is, you need two boundary conditions, and I'm going to show you cases where we can use either of these or both of these, or for the coupled case, you can show that you've got mixed of these, you've got some Neumann, some Dirichlet. And that depends on the physical conditions. Sometimes you've got to make them yourselves to see what assembly you have in front of you, what is it you're trying to solve for. So a bare assembly, for example, a bare assembly, no reflector, no nothing. For example, if I just put a sphere in the room, this will have the condition of vanishing flux at the extrapolated boundary. And the example I give my students is that imagine there's heat coming out of a room in winter, there's a heater. So some heat is going to go through the walls, and it's not going to travel for a million miles outside the wall. At a few feet or maybe a few inches outside the wall, it's going to drop down to zero. So that is what we call the Dirichlet boundary condition, that the neutrons that are leaving your outer boundary, which in this case is a bare assembly, so it's just the surface of the assembly. So this will have the condition of vanishing flux either at the physical boundary or at the extrapolated boundary. While if you go inside the thing, and if you can solve half the problem, you can cut down your effort into half by saying that there is symmetry. Remember, whenever you impose symmetry in a problem, you reduce its complexity and you improve the quality of your results, if possible. So a reflecting boundary, a reflecting surface, you can always invoke if physical conditions permit. And that's the case where you have a zero flux or a zero gradient. Zero gradient is the Neumann boundary condition, and an interface could have both flux and current continuity conditions. There's a name for this equation, is called the Poisson equation. Poisson equation. So Laplace's equation means that del square phi is 0. Poisson equation means that del square phi is S. So if I say there's no absorption, there's just a source, it becomes the Poisson equation. These are very well-known mathematical equations, and everybody knows what the solution is. So let's start with a simple problem. Okay, I'm not going to talk about numerical solutions now, a little bit later. So let's say that you have a whole core reactor design. Now, if you want to go beyond two groups, if you want to go 3 groups, 4 groups, 10 groups, 20 groups, then again you use the diffusion equation, and the problem becomes bigger and bigger, the matrices become bigger and bigger, but it's the same thing. It's just like if you teach a student to add 3 plus 5 and they say it's 8, then if I ask you what's 3,000 plus 5,000, then it's 8,000. So if you know how to solve one group and two group, you know how to solve anything. Multi-group diffusion equations. Okay, so in the multi-group form, the diffusion equation is usually used to obtain first estimates, and it can serve as a useful step for providing guesses to fulfill the transport calculations. Now, there are limitations. Whenever you write down a model, always be sure you say, this is my assumption, these are my limitations, I can solve this, I cannot solve that. Every mathematical formulation has some limitations. Okay, well, that's why you do experiments. That when you do an experiment, you're not going to get exactly, otherwise we wouldn't do experiments. So let's look at the limitation of diffusion equation. Well, first of all, it's not good near sources or boundaries. Why? Because things could change rapidly, so we've got to look at the angular flux. Now, the angular flux requires a detailed consideration. So what you need to do is don't stick to the diffusion equation. You've got to go to the transport equation. Now, the transport equation is a higher level of complexity. It's very elegant. But these days, again, you've got such powerful computation. When I was a student, we used to really look up to transport equation. Most of us did not understand it. But then came the world of computing, and now it's very common to see people who don't understand what's happening. They press the right buttons and get the right results. And I've seen so many cases where people just close their eyes, press the button, take the output, plot the graphs, color them, and get beautiful results. So that's not what we need to do. We need to understand. The purpose of this course is to understand, because once you understand, God knows what you might improve in here. And just like a lot of advancements came in the 60s and 70s, and so you can improve things even now. So there's a limitation that diffusion equation uh, is not very good near sources, not very good near boundaries. Now, you could use the discrete ordinates methods. You could use spherical harmonics. Now, when I was an undergraduate, I did my final year project on both these methods. So, so I had a very early exposure to spherical harmonics, which are based on Legendre polynomials. And I also liked discrete ordinates, but I found this to be more fun, spherical harmonics, because you can apply orthogonality in a much easier way. So let's look at table 3.1. Excuse me. So let's look at different media, different source conditions, different boundary conditions, and what do we get for the solution of the one group non-multiplying medium. Easiest, always go for a slab. Like in the previous lecture, I looked at a slab. Remember I told you that there's an infinite medium in slab geometry, there's a planar source, and that's how I explained Fermi's age equation to you. So again, I'm going to say the same thing. Let's start with an infinite slab. Now, infinite doesn't mean from one end of the earth to the other, as it means to humans. This is infinite for a neutron. Could be 5 meters even, could be 1 meter. So it depends on what's inside the medium. So let's look at an infinite. Mathematically, what infinite does is that you don't get exponentials with positive value. So you get decaying exponential. So let's solve this for a planar source at x equal to 0. And let's say that I've got a source which is emitting s neutrons per centimeter square per second. So I'm going to say that I'm not going to let my flux become infinite. So I'm going to require it to be finite. That's why when I get two solutions, e to the minus x over L plus e to the something multiplied by e to the plus x over L, that thing I'm just going to throw away, because I cannot let things go to infinity. Then the source condition, and this, let's consider that at x equal to 0, so this is a kind of a 0 to infinity problem in x. So let's say at x equal to 0, jx is s by 2. So half the neutrons are traveling right and half the neutrons are traveling left. So half right, half left. So here's the flux. Now let's look at the flux. What do I get? The flux, first of all, the x dependence looks good. I have no problem with it. It's going to be finite, it's going to die out, and at x equal to 0, the answer is SL over 2D. Now L is the diffusion length, D is the diffusion coefficient, just like we had in the Fermi age equation. The diffusion length is a measure of the distance from when it becomes a diffusion neutron to the point where it gets captured. So that's the diffusion length. Now, L square is d over sigma A. So you can simplify that further. So right now I get SL over 2D. If you know the diffusion coefficient, I'm going to give you lots of problems. We're going to have an assessment for this course. So at the end of this course, I'm going to give you problems where I could give you values of D, L, S. So I'm going to ask you what the flux is at a certain point. Let's go to 2 dimensions. Now in 2 dimensions, let's say there's, sorry, infinite slab. By infinite slab, I mean that it's finite in one direction and infinite in 2 directions. Now let's look at a planar source S. Let's look at slightly different boundary conditions from before. So we've got symmetry, and we say that at the 2 ends, A plus D, A is the physical thickness. The slab is of thickness 2A. So right side A, left side minus A, and D is the extrapolation distance, which means the physical boundary plus the D is going to give you the extrapolated boundary where we're going to say, where we can say that the flux is 0 and where we are going to say that the flux is 0. And here you can solve just half the problem. As I mentioned, solving half the problem reduces the effort and improves the accuracy. So source condition, again, the same current source, half going right, half going left. Now you want to solve this, here's what you get. That does this look finite or does it look infinite? Now in the denominator, it's okay. Now whenever I see sine hyperbolic and cosine hyperbolic, there we had an exponential. Exponential is also a hyperbolic, a trigonometric hyperbolic function. So sine h of x is e to the x minus e to the minus x over 2. So this looks good. It looks finite. There's a mod x, which means it can never blow up. Now let's look at not a source located at one position, but let's look at a uniformly distributed source, which is constantly emitting S neutrons per cubic centimeter per second. Again, it's an infinite slab of thickness 2A. So again, the boundary conditions are over here, but now I'm using symmetry. And symmetry, I'm saying that d phi by dx is 0 at x equal to 0. I get a very neat solution. Why do I say it's neat? If you put over here, you know, a plus d, x is a plus d, then you get the same thing in numerator and denominator. So 1 minus 1 is 0, and the flux conveniently goes to 0. So you can see it's correct. So these 3 solutions were for slab geometry. Now let me show you the solution of the one group diffusion equation for spherical geometry. Now in the spherical geometry, again, let's look first at an infinite sphere. Is there anything called an infinite sphere? Well, again, a mathematical idealization. Then let's look at a finite sphere of radius r. Then again, let's look at a finite sphere of radius r, but uniformly distributed sources. So again, the same thing you get over here, the same boundary conditions, finite flux phi r, source condition, but look at the source condition. Now, a sphere converges to a point at the center. So if you draw a very small sphere at the center, and the surface area of that tiny sphere is 4 pi r square, you multiply it by the current, sorry, this should be r, so you multiply it by the current jr multiplied by 4 pi r square in the limit as r goes to 0, okay, in the limit as r goes to 0, and that should give you the source neutrons. Now, why should it give you the source neutrons? Can you explain this? Why should it give you the source neutrons? Okay, now this is a question I like to ask in the exams because it tells me whether I'm being followed or not. Now, it should be 0 because in a shrinking sphere, ideally, there's nothing. When there's nothing, then a neutron is not going to lose any energy. When it's not going to lose any energy, then the source that came out is going to escape from the surface of that tiny sphere. So this is called the source condition. Now, if you do this, look at the solution, you get just like you got SL over 2D e to the minus x over L. So for a plane infinite situation, for a source, you get a very nice, neat, analogous solution to the plane one. you get SE to the minus R over L 4 pi dr. Now again, for these two cases, you can do it yourself. I think I'm going to stop over here because just to give you some time to absorb. Uh, I've seen that students absorb very well for the first 40 minutes, and then you need a little break. So I'm going to give you a break over here. So what I've done, let me just summarize. I started with the conservation equation. When I say conservation equation, it just means I'm counting things going in and things coming out. So I started with the conservation equation in 1D x, Cartesian 1D x. Then I went to, well, I haven't shown you x, y, z. I wrote down a balance equation with two variables, j and phi. I used Fick's law. I converted that into a time-dependent second order ODE, non-homogeneous. Then I showed you a two-group model for a fixed source medium, and then I showed you the solutions for these 6 cases which are in table 3.1. So I'm going to stop the lecture over here, and till we meet again, there I'm going to carry on with the diffusion.